Hey everyone, today we're going to dive into a really powerful tool from calculus, one that lets us handle functions when they get, well, a little bit messy. We are talking about implicit differentiation. It's the secret to finding the slope on some pretty tangled up curves. You know how we're all used to seeing functions in that nice, clean y equals f of x format, right? It's comfortable, it's familiar, but what happens when the equation is all jumbled up and you can't just get y by itself on one side? How in the world do you find the slope then?
Well, that question really gets to the heart of something important. Not all functions are so neatly packaged. Out in the wild world of mathematics, we really have two main types: those explicit functions we know and love, and their more tangled relatives, the implicit ones.
So on the left, you've got your standard explicit function. Y is spelled out perfectly in terms of x. But then you look to the right and you see the equation of a circle, where x and y are all mixed together. Now you could try to solve for y, sure, but you'd end up with this messy plus or minus square root situation. There's got to be a more elegant way to do this.
And lucky for us, there is. The entire technique of implicit differentiation, and I mean the whole thing, really just boils down to one single absolutely crucial trick. Let's call it the golden rule. If you can master this one concept, you've mastered the whole process.
So here it is. When you go through an equation, term by term, and differentiate with respect to x, anytime you hit a y term, you have to multiply your result by y prime. That's it. That's the entire trick. And trust me, forgetting this little multiplication step is the #1 mistake people make. It's really just the chain rule in disguise, reminding us that y isn't just a letter, it's a function of x.
And here's a perfect example of what I mean. Let's say you need to find the derivative of y squared. Okay, power rule. That gives you 2y. But wait, since it's a y term, our golden rule kicks in and we have to multiply by y prime. Bam! The derivative of y squared with respect to x is 2y times y prime. See? Not so bad. All right, theory is one thing, but let's actually see this rule get its hands dirty. We're going to go back to that circle equation, x squared plus y squared equals 25, and really put our golden rule to the test.
Okay, let's break this down together. Step 1. Differentiate everything, and I mean every single term, with respect to x. The derivative of x squared? Easy, that's 2x. Now the derivative of y squared? Hey, we just did that. It's 2y times y prime. And remember, y prime is just our shorthand for dy dx. And of course, the derivative of a constant, like 25, is just 0. So for step 2, we just need to do a little algebra to get that y prime all by itself. We'll subtract 2x from both sides, then divide everything by 2y. And there it is, our answer. The derivative, y prime, is equal to negative x divided by y.
So we did all that math and got y prime equals negative x over y. But what does that answer actually mean? Why is that so important? This is where things get really cool, and the true power of this technique shows up.
And here is the big aha moment. For a curve like a circle, the slope of the tangent line isn't just about x, it depends on the entire coordinate, both the x and the y. I mean, think about it, right? At the very top of the circle, the slope is flat, it's 0. But on the side, it's vertical, totally undefined. Our little formula, negative x over y, perfectly captures that changing relationship, no matter where you are on the curve. It's actually pretty amazing. We've basically just unlocked a superpower for calculus. We can now find the instantaneous rate of change on all these cool shapes we couldn't easily handle before. So that leaves us with one final, exciting thought. Now that we have this tool, what other tangled curves, like ellipses, and even more complex graphs can we finally analyze? The possibilities this opens up are truly exciting.